Hey, Dr. Segan here, another video lecture. Today we are going to be talking about a super important concept in science in general, and that is energy. So let's get right to it. And as we're talking about energy, we will also be talking about heat today, and how the two are related to each other. So I know when people mention energy, it's kind of got a lot of different definitions. I know my mom teaches yoga, and sometimes when I hear her talking about yoga, she's like, you have to channel your energy, and it's kind of like, what do you mean by that? Because in science, energy has a very specific definition that holds true for kind of no matter where you are. So that's kind of the energy definition that we're going to focus on today. So in science, we say energy is the ability to accelerate a mass over a distance, and another word for that is work. So what the heck does that mean? Accelerate a mass over a distance. I think we know what mass is. That just means something that weighs something, right? Something made of atoms that has a weight to it. That's mass. Distance, okay, we understand that. You can have a foot, a meter, a mile, whatever. Okay, that's distance. And then to accelerate. So to accelerate basically means to make something move faster or slower. So if you have a mass that is just sitting there, let's imagine something like a rock, and it moves, so it gains speed over some distance, that required energy. And as you know, if a rock is just sitting there, it's not going to do that by itself. Something has to move it, and that something is energy. So in simplest terms, without energy, nothing in the universe moves. Okay, cool. And that is measured in joules, which I will describe to you in more detail at our lab station.
All right, so when we're talking about a unit of energy, it's a little bit hard to wrap your head around the idea of a kilogram of mass accelerating at 1 meter per second over a distance of a meter. That's the technical definition, and what does that even mean, right? So I'm going to do a couple demos for you about energy and show you exactly what a joule is and how we measure energy in everyday objects. So I have a rock here, and I just weighed this rock, and this rock is about 1,000 grams or 1 kilogram, which means in United States terms that's about a little over 2 pounds, this rock. And I have a meter stick here, so this is a meter high off the ground, and if I were to drop this rock from this height, the acceleration due to gravity is about 10 meters per second. So over the course of a second, this rock would be moving at about 10 meters per second, or 30 feet per second. So pretty quick after it's fallen for a second. Obviously, if you drop a rock, it's moving pretty fast after a second, right? So the way this calculation works out is that I drop this rock, which weighs a kilogram, for a distance of 1 meter, and the acceleration due to gravity is about 10 meters per second. If you kind of multiply that all together, it turns out that if I drop this rock from this height, when it hits the ground, it will have about 10 joules of energy. So this right here is about 10 joules of energy. So, 10 joules of energy, is it an insane amount of energy? No. If it hits you in the nose, it might break it, so it's nothing to scoff at. We could use a smaller rock here. This rock is 1/10 the size of the other one, and it just so happens that makes our calculation perfectly to 1 joule. So this is 1 joule of energy when it hits the ground. 1 joule isn't all that much, but that just gives you a perspective of what a joule of energy looks like. Things get really weird when you think about energy. Previously in this course, I mentioned in the carbon cycle video how our body does cellular respiration, and in the process of burning sugar in our cells, we generate energy. And I demonstrated that with burning a marshmallow to show that sugar, yes, can release energy when it is consumed and burned. The strange thing about it is, if you talk about something like this candy granola bar, this chocolate granola bar here, if I look at the back of this, it says that it has about 100 calories to it. That is a unit of energy as well, and it just so happens that that corresponds to about 400,000 joules. So when I drop a little rock, if I did that 400,000 times, ground, 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 that would be the amount of energy in just this one candy bar. And if we're talking about your total energy consumption for the average human in a day, that's about 2,000 calories. That corresponds to about 8 million joules. So your body each day goes through the equivalent of energy as me dropping that rock, the small rock, about 8 million times. Ground, 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 ground. What are you doing with all that energy? It's pumping your heart, pumping your blood, running your brain, moving your body, working your muscles. All that stuff consumes a lot of energy, and it takes a lot of energy to actually run your body. So hopefully that puts energy and the units of energy into perspective for you.
All right, so that kind of helped us understand what energy is and how we measure it. It usually has something to do with motion, but not always. And that brings us to another really important concept in energy, which is the conservation of energy, which basically it works the same way as the conservation of matter, which we've discussed before in the class. It's the idea that energy cannot be created or destroyed, only transformed. And there are many, many different types of energy in the world. If you're just looking at the sun, you're talking about heat and light and also nuclear reactions. So all that is different types of energy. You might have heard of kinetic and potential energy, mechanical, chemical, thermal. All those are different forms of energy, and what they have in common is motion or the ability to make something move. So we say something has potential energy if it has the potential to make something move, even if it's not moving at the moment. For example, a stick of dynamite has a lot of chemical potential energy. There is the potential there through a chemical reaction to make something move, even though it doesn't always express that energy, if it's just sitting there on a table not doing anything. But it has the potential to move something. That technically is energy as well. So what this means is that when we say something has energy to it, if something's moving, that energy had to have come from somewhere else, and more than likely there was some kind of transformation from one kind of energy to another in that process. For example, I just dropped a rock and showed you that a falling rock has energy to it. The particular rock that I dropped had about 10 joules of energy when it reached the ground for the demonstration. But what I just taught you about the conservation of energy means that energy had to come from somewhere. Did it come from the rock? How did that energy get there? When the rock hit the ground, it had energy. I just said you can't create energy. It had to come from somewhere. Where did it come from? Me. I picked up the rock and lifted it before I dropped it. So the energy came from me. Where did my energy come from? And now you're starting to put together that almost in the same way that like nitrogen and carbon, when we were talking about how atoms move through the world and change forms, from, if we want to be gross again, we can talk about nitrogen, how it gets into the soil, and then it gets into plants, and then to animals, and then the animals poop and pee it back out, and it gets back to the soil, and it kind of moves around. Same thing with energy. You can almost kind of imagine it shifting and changing as it's moving through the world, but it's always still there. For example, we can talk about the energy that rock had as it was falling through the air. It had energy when it reached the ground. How did that energy get there? Well, I picked up the rock. If I didn't pick it up, the rock obviously wouldn't have fallen. It wouldn't have had energy. So I gave it that energy. Well, how did I get my energy? From the food I eat, and ultimately from breaking it down and burning sugar. Just like I burned that marshmallow for you guys a while back and it's showing you that sugar can release energy. Basically, your cells in your body is all designed to capture that energy and put it to work in useful ways. Where did the sugar come from that's in my body? Well, ultimately, it would have come from the plants I eat and my food. So here's our nice picture of corn, and that's where the sugar came from. Well, how did the corn get the energy to put into the sugar? Well, that came from the sun, right? That's photosynthesis. Energy goes into the corn as sunlight hits the leaves, and then that's photosynthesis makes the sugar. Yada, yada, yada. Okay, where did the sun get its energy from? Well, that's complex nuclear reactions, dependent on all kinds of different settings. And ultimately, we can trace back all energy in the universe to the Big Bang. There's no good explanation of where all this energy came from in the Big Bang. That's kind of what it points to. We also say there's the law of conservation of energy, but basically the Big Bang seems to break that law because presumably before the Big Bang there was no energy and then there was a lot of energy. So, let's not get too lost in the weeds there, but you can kind of see that energy changes form and shifts around the world. And all the energy, anytime you see something moving, that energy had to come from somewhere. That's how energy works, and energy transformations work. When we talk about energy and Earth, everything that you see moving on Earth requires energy. And that goes for every life form on Earth, every action on Earth, everything that's happening on Earth needs energy. And actually, there's only really 3 types of energy that's available to Earth ultimately. The first of these is nuclear fusion, which is basically what the sun runs off of. I'm not going to get into too much detail on the different types of nuclear reactions right now, but basically if you jam atoms together, that's called nuclear fusion, and it can release energy, heat, light, and that's what the sun's doing. And the sun powers obviously all life that's at the surface of the earth depends on the sun and sunlight for its energy through the process of photosynthesis and cellular respiration, all that. All of our fossil fuels on Earth, so this second picture here, where you see this coal is ultimately made underground after a bunch of plants have kind of been buried and swampified underneath usually swamps. So all of those things that we called fossil fuels, coal, oil, and gas, those are all made from things like algae and plants. And so ultimately that energy also, when we burn it for our electricity or whatever we're using it for, our cars, that energy is also tied back to the sun. These top 2 are kind of interesting to think about. The top picture is showing some palm trees that are blowing in the wind, and all of the reason the wind blows is because as the sunlight hits certain parts of the earth, it basically heats and cools different parts of the earth. And as you heat up things like air and water, they tend to expand. And when you cool them down, they tend to contract. And this expansion and contraction of air is basically what wind is. And so when you see the wind blowing, that's actually derived from the sunlight as well for energy. And the same goes with rain and thunderstorms and all that stuff. Those are driven by evaporation. The reason that the oceans are evaporating is because sunlight's hitting it and heating it up. So all of these things up on the top are driven by the sun. Pretty much most things that you see happening on Earth are driven by the sun. Pretty much all energy on Earth comes from the sun. With the exception of geothermal or nuclear fission-based energy. So underground in the Earth, we have all kinds of radioactive elements like uranium. We mentioned that, I think, in a previous talk. Basically, these are elements that are falling apart. They're unstable. Nuclear fission refers to when elements fall apart. So when atoms break apart into smaller atoms, that's fission. And when they're being mashed together, that's fusion. But either way, these fission reactions in Earth, well, that's what drives nuclear energy. So if we go and dig up a bunch of uranium, we can make nuclear bombs. But it's also what drives all of the geothermal heat underneath us. So all of the lava and volcanoes and plate tectonics, all that stuff is driven by geothermal energy coming from the Earth. The same goes to these funky things at the bottom of the ocean. These are hydrothermal vents, and if you go to the very bottom of the ocean where there's no sunlight reaching, the very deep parts of the ocean, you will find all kinds of life forms down there, and that's because they're living on these sort of volcanic vents, and there are special kinds of bacteria in those areas that can actually consume and make sugar out of the chemicals being released by these volcanoes. And ultimately, they are dependent on these nuclear reactions as well. And they're actually a lot more common in the world than I realized. Pretty much all over the bottom of the ocean, this stuff is living down there. And the last one that the thought occurred to me that there are scientists working on ways to harness energy from the tides. And if you don't know what a tide is, it's when the ocean water kind of goes up and down every day with the spinning of the Earth. And what's happening is the moon's gravity is actually pulling water to one side of the Earth, and as Earth spins, the water kind of spins with the Earth. But ultimately, the energy being provided there is not coming from the moon's gravity. Gravity can't do work by itself. This is actually coming from the Earth's spin, which was left over from the last supernova that's happened in our solar system. So that's just kind of a random bit of energy, kinetic energy, motion of the spin of the Earth that technically could be harnessed by organisms or by people. All right, so that kind of covers the different types of energy and how energy changes, forms from one kind to another, but is never created or destroyed. It's all kind of perplexing to think about, but that's how our world works. Which brings us to our next topic, which is going to be heat, and maybe, as I was explaining how energy changes around, you might have been asking yourself a question. Earlier, I gave the example of me dropping a rock and how the rock had energy when it hit the ground, and that was provided for by me, and that came from sugar and plants and the sun and the Big Bang ultimately. So the energy of that rock that you saw ultimately was created during the Big Bang, and it's just been kind of moving from one place to another over time. But if you were paying attention, I said that energy can't be created or destroyed. So the energy of that rock, after it hit the ground, I mean, it's not moving now. I was just looking at it a second ago. So where did that energy go? And the answer to that is heat. When that rock hit the ground, there was a bit of friction there, and that rubbing together generated a little bit of heat. And then as it was kind of bouncing to a stop, it would generate heat. Also, as it was falling through the air, obviously, it would be generating a little bit of friction and heat with that air as well. And we say for the most part, the ultimate path, the ultimate dead end of energy is always going to be something we call heat. So no matter what, eventually energy finds its way to become heat. And we'll define heat in a second, but it is kind of interesting. There's an idea of something called the heat death of the universe, which is 10 to the 106 years away. It's a really big number. But basically, the screen right here, what you're looking at, in that many years, there is a hypothesis that what you're looking at on your screen is basically what the universe is going to look like. Because the ultimate destination for all energy eventually is just kind of chaos, and that chaos is what we call heat. And so there will be a point in time where there will be no stars left in the universe, there'll be no black holes, there'll be no atoms or even matter. Everything will have kind of broken down into its most basic form, which is essentially heat. And the good news is that that is still quite a ways away, and we're not even sure if it'll ever get to that point or not. So you don't have to worry about that in your lifetime, certainly. But it's an interesting thought that physicists have had. Okay, so all of this energy ends up being heat. Well, what is heat exactly? On Earth, we define heat as kind of the chaotic motion of atoms and molecules. All atoms and molecules on Earth will move, and that's true regardless of whether they're solids, liquids, or gases. And we can kind of think of this as kind of chaotic vibrations or movements. So if we have something that's a solid, you're thinking, I don't know, the table this is on right now isn't moving, it's staying put. But if we could look very, very closely at the atoms of this table, we would actually notice that they're kind of vibrating and shaking very, very slowly. And if we were to begin adding more and more heat to this table, they would begin shaking more and more. Theoretically, and the table might not be the best example because it would eventually catch on fire. But if you have a solid substance like a metal and you keep adding more and more heat to it, the atoms of that metal will keep shaking around more and more until they can actually move around freely. And when that happens, that's what we call a liquid. So when the atoms kind of break apart, they have enough energy that they can kind of move around and flow. That is what a liquid is. And if we add even more and more heat to it, eventually they will break apart even more, and that's what we call a gas. So basically, heat energy is sort of defined as the speed of atoms or molecules in a material, and this is sort of the chaotic random motion of these atoms and molecules. Me, dropping that rock and that energy that the rock had when it hit the ground resulted in a bit of additional chaotic motion of the floor and the air of my classroom, and such a tiny amount that you wouldn't really be able to notice it necessarily, but that's what happened to it. So that energy is still here with me in my classroom, just as a tiny, tiny, tiny bit of heat. Once it becomes heat, that doesn't necessarily, it's the end of the story, because heat in and of itself has really important characteristics to it. And we actually say that heat, if you have enough of it, it can actually move. And we say there's three ways that it can kind of move in the world: conduction, convection, and radiation. Conduction is going to be our simplest way, and we'll just tackle these one at a time here. Heat energy flows. Conduction is that it's a pretty simple idea. If you have a really, really hot object and you put it next to a cold object, or they touch each other, there's going to be a direct transfer of heat from the hot object to the colder objects. This is true also of things like air and water and fluids and things like that. So if you have a hot stove in your house like this, I don't know if anybody has these old school burners anymore, but you can see the coil heats up and it gets really, really hot. Obviously, if you put a cold pan on it, then the pan gets hot. So that's the direct contact conduction. If you turn the burner off and you're no longer adding more energy to it, the burner is going to cool off, and all of that heat, where it went is that there's actually air touching that burner, and it's actually going to be heating up the air around it. And so all of that heat is still there. It's just kind of dispersing throughout the room in the air. And you kind of notice this. If you turn on your oven for a really long time in your house, you notice the house starts getting hotter. That's because the air is absorbing all that heat. That's conduction. The exact same thing actually happens in Earth. If you have something like a body of water that is really, really warm, and you have it next to some really, really cold air, the heat from the warm water will kind of dissipate into the cold air and will heat up the air. And so the tendency is that once you have heat generated somewhere, it will slowly just kind of disperse out until everything is the same temperature. And again, relating it back to that heat death of the universe idea, eventually it's just going to be kind of this one blob of nothingness of heat. That's kind of where the universe is heading. So this is actually super important for the world because there are a lot of places where this scenario happens. For example, over here in the Pacific Ocean, there's kind of a cold water current that comes this way. In the process, it makes the west coast of the United States pretty cool, climate-wise. So the air, this cold water kind of cools off the air, or I guess more accurately, the warm air kind of warms up the water. In the process, it cools off itself. The opposite is true of another part of the world. There is a kind of current of water that sort of does something like this. It's called the Gulf Stream, and it brings a whole bunch of warm water up towards Europe and Iceland and all this area. And in the process, it warms up Europe's climate considerably. It makes these the temperatures here in Europe way warmer than you would expect. We all know that as you move further north in the world, you expect things to get cooler and cooler, right? Here I am in Houston. If I start driving north into Canada, I'm expecting it to get cooler and cooler up here. But sometimes it caught me off guard. If you think about the climate of Spain, I think, Spain is a pretty nice climate. It's, not super cold or super hot. It's kind of like a nice temperate climate. If you kind of look where Spain lines up with, it lines up with like, Michigan and Minnesota. I never think of Spain getting that cold. And there's another example that I'll give you here, which is there's a place up here in the north of the United Kingdom called Scotland. So this is Scotland right here, where that X is. And we can kind of do a north equivalent over here to the middle of Canada, where you don't have any warm water oceans. It's kind of landlocked. And this is a place called Fort McMurray. And we can compare the climates of these two areas. In the winter, Scotland gets pretty cool. The average winter temperatures there are like 41 degrees. So the kind of average high temperature during the day when the sun's out in Scotland is going to be about 41 degrees in the wintertime, so in January and February. If we compare that to Fort McMurray, Canada, the high temperature, so when the sun's out and it's the warmest it gets during the day, the high temperature is -9 degrees Fahrenheit. And again, these are the exact same north-south distance, and the only difference between Fort McMurray and Scotland in terms of how much sunlight it's getting and how warm it should be is the ocean that is coming by it. So heat in our planet Earth is super important. That begs the question a little bit about why the ocean is moving in the first place. So why is this warm water moving in the ocean? And that has to do with convection. And this is a motion of heat that depends on density. Hot materials, when things get hot, and kind of like our diagram here at the bottom, as you heat things up, they begin to expand. So as you add more energy to these molecules and they start moving more and more, and they begin breaking free and more free, and they're going from solid to liquid to gas, they are expanding and they are becoming less dense. So we know that a gas is going to be lighter than a liquid, and a liquid is lighter than a solid. And the same thing happens to anything when you heat it up. And this causes a tendency for hot materials to become less dense and to rise. And cold materials tend to become more dense, they contract, and they sink. And convection is defined as the circular motion of materials based on their temperature. And our little diagrams here on the side, I think we're kind of used to thinking something like if you put oil and water together, you know, the oil will be on top of the water because it's less dense. The same thing happens with hot and cold. So if you put a hot liquid on top of a cold liquid, the hot liquid will go to the top because it's less dense. So it will rise to the top. Convection depends on the idea if you have something like a heat source at the bottom of this system, so something that's adding heat energy down here at the bottom, that means that when something touches that heat source, by conduction, it begins getting hotter, it begins expanding, and it will rise and push towards the top. If there's no heat source at the top, it will tend to cool down up here, and that will mean that it begins contracting and getting heavier over here on this part, and then it sinks back down. So this circular motion where you have heat at the bottom causing something to expand, become less dense, rise to the top, where it cools and contracts and then sinks back down, that circular motion is convection. And lots of things in the world depend on convection. For example, air, wind, and ocean currents all depend on convection. The reason why wind and ocean currents happen, why water is moving around in the world and why the wind blows is due to convection, density. Another topic that we covered earlier this year was plate tectonics and how the parts of the Earth's crust are moving around. That all has to do with mantle convection. So the lava underneath us is down here, it's really hot, and it tends to expand, and that pushes it up, and then it cools off at the surface, and that sinks it back down. That's convection of the lava underneath us, and that's what's pushing the plates of the Earth around. So all the mountains and volcanoes and all of that stuff on Earth all comes from convection. All right, our last kind of form of heat energy and how it can kind of move around in the world is called radiation. And this one is probably the hardest one to grasp, and is maybe the least intuitive of the three ways that heat can kind of move around in the world. But infrared radiation is basically a form of heat that can travel through the vacuum of space, and it's a type of what we call electromagnetic radiation. So it's similar to something like sunlight or radio waves or microwaves or the waves that your cell phone uses, those kind of invisible waves that you can't really see and that can move around in the world. Any hot object basically produces infrared radiation, and it's actually a good thing that this happens. One way you can think of this, and that maybe you have thought of this before in the world, is the idea of like an infrared goggles, if you've ever used those in a video game or something. Or if you think about snakes, certain types of snakes called vipers actually have what's called a pit organ, which lets them see in the dark. And then what they can see is actually the infrared radiation produced by things like mice. And so in the pitch darkness of the desert night, you know, this rattlesnake can actually see a mouse scurrying around based off its heat signature. That is infrared radiation. And it's actually a really good thing that hot objects produce infrared radiation. You know, if we're thinking about energy, and I said that pretty much the destination of all energy is heat, if you think about that for a second, every day we're pelted by tons and tons of sunlight, right? And every day lots of heat is released by volcanoes and all that stuff on Earth. And so if all that stuff is just turning into heat and it's not going anywhere, wouldn't we just keep getting hotter and hotter and hotter and hotter and hotter on here on Earth over time? Wouldn't we turn into a fireball before, in no time at all? And the answer is, luckily for us, the Earth, as it gets hotter, will release more and more infrared radiation out into outer space. And we call that the energy balance of Earth. And the idea of Earth's energy balance is that you have energy coming in to Earth mainly from the sun. Almost all the energy here on the surface is going to be coming from the sun. And that is balanced by infrared radiation being released back out into outer space. So basically, if you put like a snake into outer space and had it look at Earth, it could see Earth kind of like it could be seeing this mouse. Basically, Earth is releasing the same kind of radiation back out into space. And I will once again tie this into global warming, which is going to be an issue that we just keep coming back to more and more over the course of the year. Our friend carbon dioxide, which we are producing as we burn lots and lots of fuels in the world, and we said that the CO2 is accumulating more and more in the atmosphere, and the atmosphere is getting more and more carbon. What this carbon dioxide, I said in a previous lecture that it traps heat. What it actually does is prevent this infrared radiation from escaping Earth, and it keeps Earth's heat here at the surface and in the atmosphere. That's actually we call it a greenhouse gas. It just happens to interact with these infrared waves in a way that it traps this heat before it can escape Earth. So there is one last tie-in to our global warming topic. All right, so that was a lot of information, and energy is just a huge topic. And I just wanted to kind of recap the things that we learned. We learned that energy is basically the ability to do work, and that means being able to move things in the world. So picking up a rock, that takes energy. Anything that you see moving in the world, that's energy. We learned that energy can change form. So for example, it can go from sunlight to a plant to sugar that we can eat, and then we can move our body. So all that is energy changing form. And we said that the ultimate form of energy, the ultimate destination of kind of all energy, seems to be heat. So it doesn't matter what it is, eventually it's going to become heat. And once it becomes heat, it can still have an effect on the Earth. Heat tends to dissipate in any way that it can. So if you have a really, really hot area right here and surrounded by cooler areas, the heat will kind of move out into those cooler areas and kind of spread out. That's conduction. So basically, when you have contact between heat and something else, it kind of spreads out that way. Sometimes you can have these scenarios where heat, because it's less dense, will kind of push up and the cool will kind of come back down. And that's one way that heat can kind of circulate around and dissipate. And if there's nothing touching it and it can't move around like Earth is floating around in space and you have all this heat, one last way that it can kind of dissipate out into the universe is through radiation, and that's infrared radiation. And all of these things basically are pointing to eventually, and luckily for all of us watching this today, we're talking like unimaginably far into the future, what we're going to be left with is just nothing but heat. And, that is the heat death of the universe. So we'll see if humans are still around for that or if that actually ends up happening. That's more of a hypothesis at this point. But that is sort of, when you really understand energy, that's kind of where it's all going. So there's your summary of kind of energy and energy on Earth, why it's important, why is heat important, where does energy come from, all that stuff in one video. And I'm sorry that it was a little bit long, but I hope you learned something. So take it easy. Bye.